Hey guys, in this video we're going to talk about 7.6 in the textbook, improper integrals. So the first thing we need to know is, what does it mean for an integral to be improper? We're used to seeing stuff like this. So we have these bounds from 0 to 1, and maybe we're integrating some simple function. And all this is telling us is find the area under the curve x squared from x equals 0 to x equals 1. And so, we've dealt with these kind of integrals before, so these are proper integrals. But with improper integrals, we're going to look at two cases. The first case is when our lower bound is either negative infinity or our upper bound is infinity. So how do we handle something like this? If we are integrating from 0 to infinity of x squared dx, well, what does that mean? What does that mean? So, we don't have any kind of bound on the x value, so this function can go on forever and ever. And what you expect to happen to the area is that the area is also infinite, right, as we go off to x equals infinity. But it turns out some functions, when you integrate off to infinity, end up having a finite area, or a convergent area is a better way to say it. So let's just get into it and take a look at this example. So the type of improper integral, like I said, that we're going to look at first is when the limits of integration is infinite. So here we can see that we're starting at x equals 1 and we're going all the way to x equals infinity. And we want to figure out what this is. So here I have a picture on Desmos to kind of illustrate this. So we're starting at x equals 1, and we're trying to find the area under this curve all the way till x goes to infinity. Now, just based off of this picture, you can kind of see that this thing is shrinking so fast that it appears that the area is actually going to converge to some number. In other words, we don't have infinite area here. So let's prove that with calculus. And the way that we're going to do it is we're going to use limits. So this is how we set it up. I'm going to move this over here. Let's see. Okay, so this is how we set it up. To evaluate a limit like this, what we're going to do is we are going to change this guy to just an arbitrary variable b. So what we're going to write is that this guy right here is going to be equal to the limit as b goes to infinity of 1, and instead of infinity I'm changing that to b, of 1 over x squared dx. Okay? So basically we're just saying, hey, b can be this variable, and we are going to take b to get closer and closer, or rather to grow infinitely large, this area. And we want to see, when we take the limit, does the limit exist, or does this limit not exist? Does this thing diverge off onto infinity? So let's see. Well, the first thing I can do, since now I can evaluate this integral, excuse me, because I've turned this weird infinity up here into a b, and so I can evaluate this just like I would any other definite integral. So let's go ahead and do that. Meanwhile, the limit of b going to infinity is just going to hang out on the outside, and I'm left with this. So instead of 1 over x squared, I'm going to just write this as negative 2, x to the negative 2. And if I integrate this thing, if I integrate this thing on the inside, let's do that. So I add 1 to this guy, which is -1, divide by whatever that is, which is -1. And my limits of integration, I'm going from x equals 1 to x equals b. Let's go ahead and plug that in, keeping the limit in the front. And we have b to the -1 over -1 minus 1 to the -1 over -1. Now let's clean up the inside a little bit before we take this limit. So the first expression I'm going to rewrite as -1 over b. And the second expression I'm just going to write as, well, the negative is going to, this whole thing's -1. And a negative times a negative is going to give us a +1 right here. And at this point, you can take the limit. So let's go ahead and plug in infinity. I guess we can do that. And remember this guy? When the bottom gets huge, what's happening to the whole thing? The whole thing's going to 0, if you remember that from last semester in Calc 1. So this just becomes 0 plus 1, which is 1. And so the area of this infinite limit, or the area of this infinite integral, the area, we say it converges. The area converges to 1. That's what we say when the limit does exist. So going back to the picture, that kind of makes sense, right? Because we can see that starting at x equals 1, you know, this function is getting super close to the x-axis really quickly. So eventually, you know, there's the pieces that we are adding onto the area are so small that they're almost negligible. And in fact, we consider them to be negligible because we have here that the entire area from 0 to infinity is 1. Let's do another example. So we want to know, does this infinite integral, this improper integral, does it converge or does it diverge? Well, we're starting at x equals 1. So I have the graph here, and we're going all the way off to x equals infinity. And maybe you can guess what's going to happen by the graph. It looks like as x goes on to infinity, the areas aren't shrinking fast enough, right? I mean, we saw in the first example, this graph was getting super close to the x-axis really quickly. But this one, not so much. I mean, it is getting close to the x-axis, but is it getting close to the x-axis quick enough? That's what we need to prove using calculus. So let's go ahead and set up this problem with limits. So instead of evaluating from 1 to infinity, I'm going to replace infinity with b. I use b because it's the upper bound. If we were replacing something on the lower end, I would use a. Okay, so this is going to equal the limit as b goes to infinity of this definite integral from 1 to b. And instead of 1 over root x, I'm just going to write x to the -1/2 dx. Okay? So what I'm going to do is I'm going to kind of ignore this limit part on the outside of this set of orange brackets, and just evaluate that integral just like we usually do. So the limit stays on the outside, and on the inside what I have is, well, if I take the antiderivative of this guy, if I add 1 to it, I just get x to the 1/2 over 1/2, but over 1/2 is the same thing as multiplying by 2. So I'm just going to make it look a little prettier and put that 2 in the front like that. And I'm going from 1 to b, and so I'll keep that limit on the outside and evaluate this definite integral on the inside. And when I do that, I get 2b to the 1/2 minus 1 to the 1/2. Okay, let's go ahead and simplify this, I guess. Right, so actually at this point I'm going to plug in infinity anywhere I see a b. So I have 2 infinity to the 1/2, and then this thing is just minus 2. So this is 2 square root of infinity minus 2. So this thing, you know, under the radical, as numbers get really large, the entire thing is going to get really, really large. So this thing is actually divergent, okay? Because this thing is getting large without bound. So this is divergent, or you can say the limit doesn't exist. It's another way of putting it. But basically, that's what this means, is that our area is infinite. Whereas in the first example, the area was finite because it converged to a number 1. So we want to evaluate this improper integral from 0 to infinity of e to the negative 5x. So looking at the picture, we're starting at x equals 0, and we're trying to find all of the area under the curve bounded by the x-axis. And so, you know, you can probably guess that this thing is going to converge, right? Because the function is getting super close to the x-axis very quickly. But let's go ahead and prove this with calculus. So we're going to set up our limit problem. We have the limit as b goes to infinity of 0 to b e to the negative 5x dx. All right. So what I'm going to do to evaluate this definite integral is I'm going to make a u substitution. So I'm going to let u equal negative 5x, and therefore du is going to equal negative 5 dx, and isolating dx, that equals du over negative 5. All right, so let's go ahead and rewrite this. Limit as b goes to infinity, and I'm going to just bring out the negative 1 over 5. I hope that's okay. 0 to b e to the u du. Okay. From here, I know that when I integrate e to the u, it's still e to the u. So this becomes limit as b goes to infinity of negative 1 over 5 e to the u from, and we're integrating from 0 to b. Okay, excuse me. And if I go ahead and plug back in my u, which was negative 5x, I'll go ahead and do that now, and then I'll evaluate this thing. So what I have is the limit as b goes to infinity, negative 1 over 5, e to the negative 5b minus e to the 0, right? So simplifying this to 1 and then distributing the negative 1 over 5 in there. All right, so let's see what I have now. Well, actually, this should be 1 over 5, not 1, right? Because I'm multiplying negative 1 over 5 times negative 1. And at this point, what I can do is I can put this in the denominator in the following way. So this is going to be 1 over 5e to the 5b plus 1/5. And at this point, I can go ahead and put that infinity in to give me 1 over 5e to the 5 times infinity plus 1 over 5. Now this guy is getting humongous, right? So that means this whole thing is going to 0. So we have 0 plus 1 over 5 is equal to 1 over 5. And so this guy, this integral is going to be convergent. And the area it converges to is 1/5. So a neat little trick that we can use is if our interval, if our limits of integration are from negative infinity to positive infinity, we can break it up by using a number in between those concepts, negative infinity and positive infinity, to break up the integral in the following way. So with this problem, we're integrating from negative infinity to infinity. So we want to chop up this interval to include a real number, c, like we have right here. So let's go ahead and figure out if there's any issues with the denominator. If there is any issues with the domain, then it's a good idea to chop it up in those spots. But let's see, if we have 1 plus e to the 2x, we don't want this to equal 0, right? That's our domain restriction here. And if we isolate e to the 2x, well, we get e to the 2x can't equal negative 1, but that's never going to happen with real values for x. So basically, we don't have any problems here. What I'm going to do is I am going to just choose a random number that is nice. The number that I'm going to choose is 0. So the idea is to find the area from negative infinity to 0, and then from 0 to positive infinity. Now, I don't have to pick 0. I could pick, 10, 20, 30, whatever number you want. It doesn't matter, but I'm choosing 0 just because it's easy. So I'm going to go from negative infinity to 0, find the area under this curve, plus, and then I'm going to go from 0 to positive infinity. And I forgot my dx on the purple, but okay. So let's go ahead and write this in terms of limits. So for the purple, we have the limit. Now, this time we want to replace negative infinity, our lower bound, and so I'm going to use a in replacement of the lower bound. So we're taking the limit as a goes to negative infinity of a to 0 of this function, and then plus this other guy, this time I'm replacing the upper bound, so I'm going to take the limit as b goes to positive infinity of 0 to b, that's what I'm replacing in there. All right. Okay, so now to evaluate this guy in here, what I'm going to do is I'm going to use a u substitution. So I am going to let u equal e to the x. Therefore, du is e to the x dx. And so dx is simply du over e to the x. All right. So let's put this off to the side here. And carry this down, so we have a to the negative infinity. Okay, so I'm replacing e to the x with u, so I have u over 1 plus u squared, and dx is du over e to the x. And what's neat about this is this guy is the same thing as u, right? We just made the substitution here. So I can replace that with u. Let's do that. And I'll just carry everything else over just to be neat. This is the same exact integral, so I'm just gonna do the same thing. And these u's will cancel pretty nicely to just give me 1 over 1 plus u squared. So let's do that. Okay, so now I'm going to use the integral table. Now, let's get it out and see which one we're going to use. So it appears that to integrate this guy, we can use, in the integral table, we can use 5-24. So that's what I'm going to use to integrate this thing. And of course a is 1 in this case. So we have the following. We have tan inverse of u over 1, which is just u. All right, cool. So let's go ahead and replace u, e to the x back in for u. So right here, before we evaluated our bounds. All right, let's see what we get. So leave this limit on the outside. And on the inside, when I evaluate this thing, I get tan inverse e to the 0 minus tan inverse e to the a. Same kind of story over here. Tan inverse, this time e to the b, minus tan inverse of e to the 0. All right, so that's what I have so far. This, running out of room here, but let's go ahead and clean up the inside before we put our infinities in. So tan inverse of e to the 0, well, e to the 0 is the same thing as 1. And tan inverse of 1 is the angle that has a tangent of 1. That's pi over 4. All right, so now I'm going to go ahead and replace this guy with negative infinity. And what I end up getting is, for this purple part, the purple part, I just get pi over 4 minus tan inverse of e to the negative infinity. And then over here, when I evaluate at b approaches infinity, I get tan inverse of e to the infinity minus, and then this part, this is again tan inverse of 1, which is pi over 4. That's cool. All right, nice. Well, something nice here is, let's see, what's nice here? These guys cancel. And I'm simply left with negative tan inverse e to the negative infinity plus tan inverse of e to the positive infinity. Well, this guy, e to the negative infinity, is the same thing as 1 over e to the infinity, which we know goes to 0 as the bottom gets big. So this actually goes to 0 here. All right, now tan inverse of 0 is simply 0. The angle 0 has a tangent of 0, so this all goes to 0. And we're simply left with tan inverse of e to the infinity. And, you know, e to the infinity, well, that's just going to go to infinity. And so the answer here is going to be pi over 2. Now, we can see this in a few different ways. You know, why is it that the tan inverse of infinity is pi over 2? What the heck does that even mean? Well, tan inverse is either going to be in quadrants 1 or quadrant 2, between negative pi over 2 and pi over 2. And basically, you know, tangent going to infinity is telling us that our denominator, our y over x, our x is getting really, really small to make this thing blow up, right? When the denominator gets super, super small, the entire fraction y over x blows up. So you can imagine, you know, this x value, this x value right here is getting smaller and smaller, and the angle that it's approaching is pi over 2. That's one way to see it. Another way to see it is to put this function in Desmos, tan inverse. Let's do it. If we put in tan inverse, so the tan inverse function, well, we can see what happens when x gets bigger and bigger and bigger. When x gets bigger and bigger and bigger, we follow this thing, and it seems to converge on pi over 2, which is close to 1.57. Right? As we get bigger and bigger, this thing seems to converge on pi over 2. And notice that, you know, tangent is undefined at pi over 2. So that is one way to see this. Let's go ahead and do another example that's sort of similar. All right. So we are trying to break this thing up. We're going from negative infinity to positive infinity, and we're trying to integrate this function 1 over z squared plus 25. Okay, so again, I don't have any issues with the denominator. I don't want the denominator to be equal to 0, but when I try to figure out where the problem is, I end up getting that the problem is at a complex number. Right? And we don't care about that here. We're talking about all real numbers. So what I'm going to do is I'm going to break it up just like I did the previous one, from negative infinity to 0. So we're going to go, and what color did I use? Purple? Yeah. Let's be consistent with that. So we are going from negative infinity to 0 of this function, trying to find the area under this curve, dz, plus, and then we're going to start at 0. We're going to start at 0 and go up to positive infinity, find the area under this function. And the reason we're parsing this up is so that we can use those definite integrals to actually get an answer here. So let's go ahead and use my limit definitions. So for the purple part, I have the limit. Well, here I'm replacing the lower bound. So I have the limit as a goes to negative infinity of negative infinity to 0 of this guy. All right, plus same thing. Now I'm replacing my upper bound. So I'm going from b, I'm approaching infinity. B is approaching infinity of the same thing. From 0 to infinity. 1 over x squared plus 25. Oh, not x squared. I meant to do z squared. Sorry, guys. Z squared plus 25. And here I have, again, z squared plus 25 dz. All right, so how do I tackle this? Well, I have to figure out what, and actually I need to replace this with A, and I need to replace the other one with B. I'm not sure why I didn't do that, but let's go ahead and evaluate these definite integrals. So the first thing we should recognize is that, again, we have a squared plus a variable squared in the denominator. So again, we're going to use the same thing in our integration tables we used for the previous problem, which is 5-24. This is what we're going to use, okay? And so how this is going to work is we're just going to replace it in here. We have the limit going to negative infinity, and the integral, when I evaluate this, let's see what I get. I get the following. I get 1 over 5, because a is 5, tan inverse of z over 5. And I'm going from a to 0 here. All right, so let's just put that in our pocket for a second. Let's do the other one. Just keep everything organized. This is how I like to do things. But we get the same thing because it's the same integral here. We haven't evaluated the bounds yet. This time we're going from 0 to b. All right, cool. Okay, so let's see. What could I do? I'm going to go ahead and plug in my bounds for purple, leaving that limit just hanging out on the outside. So my first one, I have a 5th tan inverse of 0 over 5 minus a 5th tan inverse of a over 5. Beautiful. And I have a similar situation over here. Will I be able to make room? I don't know. So over here I have a 5th tan inverse of b over 5 minus a 5th tan inverse of 0 over 5. Beautiful. All right, let's go ahead and clean it up. So this thing is tan inverse of 0, which is just 0. So this whole thing clears to 0. That's what I'm going to put here. So this whole thing clears to 0. This is before I'm plugging any kind of infinity in. Same thing over here. This thing clears to 0. So let me write this a little bit better. So I have the limit as a goes to negative infinity of negative a fifth tan inverse of a over 5 plus, now I forgot my limit down here, but plus the limit as b goes to infinity of a 5th tan inverse of b over 5. All right, so from here, I'm going to plug in my negative infinity in purple, and I'm going to plug in my positive infinity for orange for the variables. So for purple, I end up getting negative a fifth tan inverse of negative infinity over 5 plus a fifth tan inverse of infinity over 5. And let's make sense of what this is. So this guy is going to just go tan inverse of negative infinity over 5. Negative infinity over 5 is simply negative infinity. So let's replace that. And over here, infinity over 5 is simply infinity. So let's replace that. So in the previous problem, we saw that tan inverse of infinity was pi over 2. So this whole thing is going to be a fifth times pi over 2, which is pi over 10. All right. So this whole thing goes to pi over 10 in orange. And over here, well, for a very similar reason, tan inverse of negative infinity, as this thing goes to negative infinity, this thing is going to approach negative pi over 2. Okay, and again, we can see that on the curve. As we are moving to the left in the x direction, this tangent inverse, right? This tangent inverse is approaching negative pi over 2, as we can see, because negative pi over 2, if we put it in here, let's put it in, negative pi over 2 is going to be negative 1.57 and some change, and we can see that that is what this thing is going towards. Okay. Another way to see it is with the triangle, and yeah, so that is that problem. So this guy is going to negative pi over 2. So we have negative a fifth times negative pi over 2 is going to give us a positive pi over 10. So that's what purple is. Purple is positive pi over 10. And can't even speak. I'm so excited. So pi over 10 plus pi over 10 is going to be 2 pi over 10, which simplifies to pi over 5, okay? So here we have a converging area, which is crazy because we're integrating from negative infinity all the way to positive infinity, and somehow we still end up getting a finite area of pi over 5. It's pretty freaking cool if you ask me. All right, so some of the examples in your homework have this sort of language, and you should just kind of just evaluate the integral. That's all I really want you to do. And yes, you may have to use L'Hopital's rule, which I will remind you of, but at the end of the day, just do what we've been doing. All right, so here's what we gotta do. We see that we have an infinite upper bound for our integral. So, we do our thing. We replace this with the limit. Instead of infinity, we're going from b approaches infinity of the following. We're going from 1 to b, and we're trying to integrate this guy. So take a moment and think, how would you integrate this thing? I think a u substitution is easy here. Let's do that off to the side. So we're going to let u equal 5x plus 2, and therefore du is equal to 5dx, and dx is equal to du over 5. All right, so let's go ahead and make those substitutions in here. See, for the dx, I'm putting this guy, and for the u, I'm putting, or for the 5x plus 2, I'm putting u. All right, cool. So what I'm going to do from here is I'm going to pull the 1/5 out of out of the integral. So let's do that. We got the 1/5 chilling on the outside right there. And we know what the antiderivative of 1 over u is. That's just ln of absolute value of u. So let's write that out. And I'm going to go ahead, before I plug my bounds in, I'm going to plug in what u was, which was 5x plus 2. So that's coming in here. All right, now I can go ahead and evaluate on my bounds. So I have ln of 5b plus 2 minus ln of 5 times 1 is 5 plus 2 is 7. So let's just save some time and just put that. All right, and let's go ahead and plug in infinity for b. All right, so clearly anything times infinity is infinity. This whole thing goes to infinity. So this is a 5th ln of infinity minus a 5th ln of 7. All right, so what is the ln of infinity? Well, that's just going to be infinity, right? So this goes to infinity. Infinity minus just a number, of course, is going to be infinity. And so what this tells us is that the area is not finite. The area is divergent. Okay. Calculate the integral if it converges. You may calculate the limit by L'Hopital's rule or other methods. So since we have an improper integral, we need to set up our limit problem. So this turns into the limit as b goes to infinity of 0 to b 1 over x minus 1 squared dx. From here, I'm going to go ahead and make a u substitution. I'm going to let u equal x minus 1. Therefore, du is equal to dx. And now I'm going to make those substitutions. All right, so far so good. Now u squared is the same thing as u to the negative 2. So when I integrate this guy, remember I'm adding 1 here and dividing by negative 1. So knowing that, we have this guy, and we have negative u to the negative 1, and our bounds, our lower bound is 0 and our upper bound is b. Let's go ahead and plug in u. So u is equal to x minus 1. So actually, negative u to the negative 1 is just the same thing as negative 1 over u. So let's write that first. So then we have the following. We have negative 1, and u was x minus 1. And we're going from 0 to b. Okay? So keeping that limit on the outside, we have negative 1 over b minus 1 minus negative 1 over 0 minus 1. Just evaluating at those limits. cleaning this up a little bit, we get -1 over b minus 1, and then this is +1, a negative and a positive, make a -1. All right, finally what we're going to do is we're going to plug in infinity for b. And of course, this thing is going to get huge without bound. So this thing goes to 0. 0 minus 1 is going to give us -1. All right, so what is that telling us here? That's telling us that the majority of the area is going to be below the x-axis because of that -1. Okay. All right, let's go ahead and do this example. So again, we're trying to see, does it converge? And by the way, I didn't say this, but this converges because the limit does exist there. Converges to -1. Okay, let's go ahead and do this one. So what I'm going to do is I am first going to rewrite this so that we have a limit problem. We're going from, so we're approaching infinity, b is approaching infinity, from 0 to b, and I'm going to rewrite this a little bit. I'm going to write this as x e to the -x dx. Okay, so pulling back some knowledge that we learned a couple of weeks ago, I'm gonna do integration by parts here because I have a product of two functions that, you know, u substitution is not going to be appropriate here. So let's go ahead and do integration by parts. You guys hopefully remember this. What integration by parts says is that, you know, if we have this product, if we have the integral of u dv, that's going to equal u times v minus the integral of v du. So we have to pick a u that gets simpler when we differentiate it. So I think the easiest thing to do is to say that x is going to be u, and then the rest is going to be dv. All right, so let's write that up here. So du is just dx. And actually, let me just kind of move this over a little bit. And then, so dv was the rest of it. So dv was e to the -x. And v, if we integrate e to the -x, well, what do I have to take the derivative of to get this? I have to take the derivative of negative e to the -x, right? When I take the derivative of this guy, chain rule, take the derivative of the outside times the derivative of -1x, which is -1. So these two negatives give us that positive e to the -x. All right? So, okay, so moral of the story, negative e to the -x is v. Let's put that over here. All right, so let's go ahead and do this guy. All right, so we have, I'm going to do it down here, we have limit as b goes to infinity of, okay, so, you know, using integration by parts here, we're just plugging in everything into this formula that we have in red. So we have u times v is just going to give us -x e to the -x, that's u times v, minus integrate v du, which is just dx. That's nice. And what were our bounds again? We're going from 0 to b. Beautiful, beautiful, beautiful. All right, cool. So what I can do here is I can pull out this negative first of all. And the next thing I have to do is integrate e to the negative x, which we already did up here. So the antiderivative of e to the negative x is just negative e to the negative x. All right, cool. So let's do that. So we have this, negative x, e to the negative x. And then we just said that this guy is going to be negative e to the negative x. Didn't plug anything in yet. That's my last step here. Okay, so let's do this. So we have, all right, so plugging in b first, in for x, we have negative b, e to the negative b, minus e to the negative b, all right, minus, now we evaluate at 0, minus 0, e to the minus 0, minus e to the minus 0. Beautiful. Okay. Since I know that I'm about to need denominators to, when I plug in infinity, I'm gonna just, you know, do this ahead of time. This thing is just negative b over e to the b, minus, this thing is just 1 over e to the b, minus, this all goes to 0 right here. E to the negative 0 is 1, so this is just minus 1, which becomes a positive 1. Put that in here. Okay, so far so good, I believe. Okay, so what I am going to do from here is I'm going to use that limit property that says I can take the limit of each individual piece in here, and that's what I'm going to do, and you'll see why I'm doing that in just a second. So I have this e to the b minus limit b goes to infinity of 1 over e to the b, and of course the plus 1, you know, the limit of that, we don't have a b, so it's just plus 1. We don't have to worry about it. Now over here, I'm going to pull that negative out in the front. I'm going to pull that negative out in the front. This guy, when I go to infinity, this thing goes to 0. So this is just minus 0 plus 1, which is just plus 1. Let's just take care of that. And let's see. Okay, so, okay, here we go. So remember, if I plug in infinity here, what I end up getting is infinity over infinity. Do you remember that? Do you remember from Calc 1? This is when we use L'Hopital's rule, right? That was from Calc 1. And what we did is we took the derivative of the top and the bottom. Here we're doing it with respect to b. So, okay, so using L'Hopital's rule, this becomes negative limit, b goes to infinity. Derivative of b is simply 1. Derivative of e to the b is just e to the b. And then we go ahead and plug in infinity and see if we get anywhere here. So this is going to give us negative 1 over e to the infinity. And of course this goes to 0, right? So our answer here is 1. And yes, this is convergent because it converges to 1. Okay, so we want to integrate 6e to the negative square root of x from 0 to infinity. So let's set up our limit definition. We have our upper bound is infinity, so we're approaching infinity, and we're taking the limit from 0 to b. I'm actually just going to bring the 6 on the outside by using those limit properties. So let's actually do that. So we're going to do 6 limit as b goes to infinity from 0 to b of e to the negative root x dx. So from this point, I am going to do a u substitution, and this is going to be one of those problems where we have to use integration by parts as well. So from here on out, I'm going to do w substitutions instead of using the letter u. So what I'm going to do is I'm going to let w equal negative root x, or sorry, let's actually let w equal positive root x. And therefore dw, if I take the derivative, is just 1/2 x to the negative 1/2 using the power rule, dx. And solving for dx, if I divide both sides by half, I just get 2 dw. It's the same thing as multiplying by 2, dividing by a half, divided by x to the negative 1/2. Now x to the negative 1/2 is the same thing as just the square root of x in the numerator. So this is this, this guy is just 2 dw, and then we can bring this x to the negative 1/2 above to x to the positive 1/2. Now, the square root of x is w, so that's what I'm going to replace this guy with. All right, and so this is supposed to be dx. So dx is equal to 2w dw, and I can replace that in here. So let's write that out. We have 6 limit b going to infinity of 0 to b of e to the negative w, and instead of dx, I'm replacing 2w dw. Now I'm going to bring the 2 all the way on the outside. Okay, so here's where I'm at so far. Now this guy is just going to be a 12 on the outside. Limit b goes to infinity of 0 to b e to the negative w w dw. All right, so this is when integration by parts comes in, because we have a product of functions and we can't use u substitution to simplify this anymore. So we got to use integration by parts. So what I'm going to do is I'm going to let u equal w, therefore du is just dw, and the rest, if you remember how we did this, we picked the u to be the easier function, or the function that gets simpler when you differentiate it, and we picked dv to be the other function. So here dv is equal to e to the negative w, and if I integrate that guy, so if I integrate e to the negative w, that's just going to give us negative e to the negative w, right? When I take the derivative of this guy, I get exactly this. So this is going to be negative e to the negative w, and now I can go ahead and use integration by parts. So remember what integration by parts says. It says that we take the integral of a product, u dv, and that equals uv minus the integral of v du. So in this case, we had u equal w and dv equals e to the negative w in our little product here. So let's go ahead and replace what we can. Now, in the inside of these brackets, I'm going to apply integration by parts, the right side of that formula. So we have u times v, which becomes, maybe I'll do it in yellow actually. We have u times v is negative w e to the negative w minus integrate v du. Okay, so before we put in our limits of integration, I'm going to evaluate this completely, this integral right there. That guy is just going to be, well, what we can do first is we can pull out a negative sign. Let's actually do that first. So negative e to the negative w. I can just pull out that negative sign right there. And I can see that we've already found the antiderivative here. We've found it many times in several problems that we've done. It's going to be negative e to the negative w. So let's write that down. Okay, so I'm just replacing this with negative e to the negative w. And I'm going to go ahead and plug in what w was when I made my substitution. Remember above what we first did, w equals the square root of x. Let's write that down here. All right, so rewriting this a little bit nicer with denominators, I have negative root x over e to the root x, if I just bring that to the bottom, minus 1 over e to the positive root x. Again, just bringing this guy to the bottom from 0 to b, and now I'm going to evaluate at my limits of integration. So I still have that 12 limit b going to infinity on the outside. Then I plug in b first for x, so I have negative root b over e to the root b minus 1 over e to the root b. Minus, now I plug in 0. Well, this all goes to 0, so I have 0 minus 1 over e to the 0, basically. So this just becomes 0 minus 1 is minus 1. Let's put that in there. Okay. Now what I'm going to do is I am going to factor out a negative sign, bring it all the way to the front using properties of limits. And when I do that, what I'm left with on the inside, I'm taking a negative sign out of everybody. Everybody gets a negative sign taken out. So when I do that, I get root b over e, root b, plus 1 over e, root b. This actually, becomes a positive. Let's actually write that up here. So if I take a negative away from it, I have to replace that with a negative. So let's clear off some stuff. Let's clear off this stuff. Make some room. Making some room. All right, let's see what we got here. All right, y'all, here comes the limit. So if we plug in infinity for b, this first one, if we plug in infinity right here, e to the square root of infinity, that goes to 1 over infinity, which becomes a 0. So let's replace this with 0. Now this guy, we're going to have to use L'Hopital's rule, because if I plug in infinity for b, I get root infinity over e to the root infinity is indeterminate form. So here I'm going to use L'Hopital's rule, and that tells me to take the derivative of the top. So the derivative of root b is just 1/2 b to the negative 1/2. And then I take the derivative of the denominator. So the derivative of e to, and I should actually be taking this with respect to b. Let's change that here. This guy, I have to use the chain rule. So this is just e to the square root of b times the derivative of the inner function, which is square root of b. The derivative of that we just found, 1/2 b to the negative 1/2. All right, so when I use L'Hopital's rule, I can replace top and bottom with what I just found here and here. So let's do that. And we can see that these guys are going to cancel, and I'm just left with 1 over e to the root b. And when b gets huge, when we plug in infinity again, that thing is going to go to 0. We have 1 over infinity, that goes to 0. So this guy goes to 0. And what we're left with at this point is just negative 12 times negative 1 equals positive 12. So this is my answer, you guys. So we just looked at improper integrals that were improper because the limits of integration were either negative infinity or positive infinity. So these guys were either negative infinity or positive infinity. We're now going to look at a different type of improper integral. So if you look at our example here, this integral is improper, and you wouldn't think so at first glance because the limits are 0 and 1, which are not infinite. But the issue here is that we have a problem with the integrand, the function that's being integrated, right? We have a problem within those numbers from 0 to 1. And so the first thing we need to do is we need to figure out where is the problem in this interval from 0 to 1. And the only way that we have issues with this function is if the denominator is equal to 0, right? So, you know, we can't have a function be defined when the denominator is 0. So here we have the square root of x cannot equal to 0. So that's a problem, right? Because if we look at the function, we see that, you know, that 0 is represented by a vertical asymptote, and you know, we want to know what's happening to the area here. Is it converging to some kind of number between 0 and 1? Or is it diverging? I mean, clearly, you know, this is all good because it's bounded, but then at 0 it becomes unbounded, right? This thing goes up forever and ever. And we want to investigate what's going on there. So that's what I'm going to insert an A right here in with our problem area because that's the lower bound, A. So I'm going to take the limit as A goes to 0 of A to 1, again my problem area, and then this is the same thing as x to the negative 1/2 dx. Now all I care about is what's happening to the limit as A approaches 0 from the right side, right? Because, you know, we don't care about the area on the left side of 0. Our interval is from 0 to 1. So let's go ahead and figure this out. All right. So this is a pretty simple integral to evaluate. All we do is add 1 and divide by whatever we get when we do that. So when we do that, we do x to the 1/2 divided by 1/2, which is the same thing as multiplying by 2. And we're going from A to 1. So evaluating at these limits, I have 2 times 1 to the 1/2, or square root of 1, minus 2 times A to the 1/2. All right. And let's carry this stuff down. So we have limit as A goes to 0 from the right. So what's happening to the area as a gets really close to 0. So like maybe we should look at the picture a little closer. So we're starting here, right? Our bound is from 0 to 1. So if we're approaching 0 from the right, we start at 1. And then, you know, maybe a equals 1/2. And so we look at this area, okay? And then a gets even closer to 0. So maybe 1/4. And we look at this area. And we're getting super, super close to 0. And we're seeing, does this area go off to infinity, or does it converge to some sort of number? Okay. So that tangent's over with. So we have 2 minus 2 root a. And if I go ahead and plug in 0 for a at this point, I get 2 minus 2 root 0, which equals 2. So convergent. So this guy is converging to 2. So yes, we are considering this this area from 0 to 1 to be convergent. Okay, let's do another example. So what I'm going to do is I have the graph to the right, and I'm going to figure out what's the problem area. Well, look at our denominator. What can the denominator not be from 0 to 2? Well, it can't be 2, right? That's going to cause the denominator to be 0. So my asymptote, my problem area is at 2. So that's what I'm going to replace with b, since it's the upper bound. So this becomes the limit as b approaches 2, and we are approaching 2 from the left because we're starting at 0 and we're interested in what's happening from 0 to 2. So we are approaching 2 from the left. As you can see here, we're trying to see what happens to the area there. Okay, cool. So this is going to be from 0 to b of 1 over x minus 2 squared dx. Now I'm going to do a u substitution, and actually I'm going to call it a w substitution from now on, just in case we need to do an integration by parts within the substitution. So I am going to let w equal x minus 2. And therefore dw, if I take the derivative of x minus 2, I just get dx. So let's replace that in here. All right, beautiful. Let's go ahead and figure out what this guy's going to be. This is the same thing as w to the negative 2. So when I add 1 and divide by 1, or divide by negative 1, I get that this is the antiderivative of this guy. So I have the limit as b is going to 2 from the left, and this is going to be w to the negative 1 is 1 over w, so this is negative 1 over w, and we're evaluating from 0 to b. And w, before I do this, I'm going to just plug in my x minus 2 back in for w. Evaluating at my limits. All right. So if I take the limit as b goes to 2 from the left, well, if I were to plug in 2 into this, I'm getting an undefined answer, right? Which is an issue because here I can't really do anything. I can't use L'Hopital's rule. You know, this thing is going to not exist at 2, right? So here the limit doesn't exist, and we can actually see this in Desmos too. Just think of this as f of x equals negative 1 over x minus 2. And let's look at what happens as the limit goes to 2 from the left of this guy. Let's just look at it. Negative 1 over x minus 2. So all right, so as we can see, as this function, as this red curve is getting closer and closer to 2 from the left side, this thing is going off to infinity. We can see that. So that's another way to prove to yourself that this limit does not exist right here. Since that's the case, this whole thing is divergent, right? If it doesn't exist in one spot, this negative 1/2 we don't even care about. So what we say here is this thing is this is divergent. This is divergent. All right, let's do this. Investigate the convergence of 1 over x to the 4th dx. All right, so we are trying to find the area under this curve from x equals negative 1 to x equals 2. So right here all the way to here, and we can see that there's a big problem somewhere. Where's that asymptote at? That asymptote is at x equals 0, all right? So that's the issue. We're gonna have to chop up this integral because 0 is not at one of the endpoints. 0 is the problem, right? So instead of writing negative 1 to 2, what I'm going to write, I'm going to go from negative 1 to the problem area plus the problem area 0 to 2. Right? I chopped it up because neither negative 1 nor 2 are issues. It's 0, that's the problem. So what I want to do is I want to turn both of these into limits, right? So here I'm replacing that guy with b because it's the upper limit. So this is going to be the limit as b approaches 0. And I'm approaching 0 from the left here, right? Because I'm coming up from the left, if you can see that on the graph. Okay, and then we're going from negative 1 to b of 1 x to the 4th dx plus, in orange, we this time our lower limit is the problem, so I'm replacing that with a. And we're coming from the right. All right, so let's see what's happening here. Okay, so let's see this guy and this guy. Well, so 1 over x to the 4 is x to the negative 4. The antiderivative is going to be x to the negative 3 over negative 3. right? So this guy, we have the limit as b goes to 0 from the left of negative x to the negative 3 over 3, negative 1 to b, and same antiderivative for the second part, but our limits of integration are going to change. So we are going from a to 2. All right, so for this first one, b goes to 0 from the left, and then we have negative b to the negative 3 over 3 minus negative 1 to the negative 3 over 3 and then for the second one we have negative 2 to the negative 3 over 3 minus negative a to the negative 3 over 3. So far so good. And let's see what is happening here. I can clean this up, so let's actually clean this up as much as we can before we start evaluating our limits. On the inside here, I have negative 1 over 3b to the third. I like to have that variable in the denominator to see if this thing goes to 0. Minus, and then negative 1 to the negative 3 is just negative 1 over 3, and then negative 1 to the 3, like that. Negative 1 to the third is negative 1. Negative 1 over 3 times negative 1 is just a positive 1/3. So this is just going to be a positive 1/3. That's nice. And then over here we can kind of do the same thing. So inside, let's see what I have. I have negative 2 to the negative 3. Well, I can bring that 2 to the negative 3 down. And then over here, I can do a similar thing. Now the issue here, if one part of this limit is divergent, so for example, if this yellow thing ends up diverging, then we don't even have to worry about this part, because if one part is divergent, the whole thing is divergent. So if I plug in 0 into this guy, right, I still have a problem. I still have a limit that doesn't exist. And you should check Desmos to just, double convince yourself that this limit does not exist. So this limit, when b goes to 0 from the left, does not exist. Negative 1 over 3x to the third. Let's look at it. So as I approach 0 from the left, we can see that this thing is growing without bound. And so for that reason, again, the limit does not exist. Okay, so since that is non-existent, this whole thing is divergent. So we want to integrate the function 1 over x minus 4 to the 2/3 from x equals 0 to x equals 6. So there's going to be an issue here, and that issue happens with the denominator. remember, we can't have a denominator equaling 0. So our little equation here is x minus 4 to the 2/3 can't equal 0. Let's go ahead and solve for x. If I raise both sides to the 3/2, well, that goes to 1, cancels out basically. X minus 4 cannot equal 0 to 3/2, it's just 0. So here we add 4 to both sides, and x cannot equal 4. That's our problem area. So we gotta break up this integral into two parts that involve 4. So starting at the bottom, we're going from 0, then we stop at 4. Integrate this guy. All right, and then we're going to add on 4 to 6. Okay. So let's set this up in terms of limits. So the first one, our 4 is in the upper bound, so we're going to replace that with b. I like b for the upper bound. So let's say the limit as b goes to 4 of this integral. And we're going from 0 to b. Plus, this time our lower bound is 4. So I'm going to say the limit as a this time, as a goes to 4. And I'll replace the lower bound 4 with a. Now for this one, are we approaching 4 from the left or the right side? Well, we're approaching 4 from the left side, right? Because we're going from 0 to 4. Here, we're coming from the left. And over here, we're approaching 4 from the right side for a similar reason. All right, perfect. So let's go ahead and evaluate these integrals. So I'm going to actually do a u substitution, which I'm now calling w. So I'm going to let w equal x minus 4, and therefore dw is just equal to dx, taking the derivative of both sides. So let's replace that. All right, so this is a pretty easy antiderivative to find, this 1 over w to the 2/3. So this is the same thing as w to the negative 2/3. And so if I add 1 to it, if I add 3 over 3, I get w to the 1/3 over 1/3, which is the same thing as 3w to the 1/3. All right, so let's go ahead and do that here. All right, so far so good. Now w was originally, when we made our substitution, w was x minus 4. So I'm going to sub that back in before I evaluate. Okay. So evaluating this thing, I get 3 times b minus 4 to the 3rd minus 3 times 0 minus 4 to the 1/3. Okay. All right, cool. So let's go ahead and evaluate our limit. So we're plugging in b is equal to 4, right? So let's do that. If we plug in 4 in for b, then this whole thing becomes 3 times 0 to the 3rd minus 3 times negative 4 to the 3rd. And I'm going to do the same thing over here. I'm going to plug in 4 for a. So this becomes 6 minus 4 is 2 to the 3rd minus 3 times 4 minus 4 is 0, 0 to the 3rd. Well, 0 to the 3rd is 0. That goes to 0. This goes to 0 as well. So I'm just left with negative 3, negative 4 to the 1/3 plus 3 times 2 to the 1/3. And if I put this in the calculator and get a decimal for it, I'm going to end up getting 8.542 as my answer here.